All right, next up we have Hess's law. So Hess's law is yet another way of determining the delta H for some reaction. So we've already seen several ways. There are many, I think 6 or 7 different ways of calculating delta H for a reaction, depending on what you're given. Keep in mind that the delta H for a reaction is the same whether it occurs by one step or a series of steps. So delta H is a state function, meaning its value is independent of pathway taken. So as we see here, delta H for a reaction could be found by taking the sum of the delta H's of the steps. So I just put it as A, B, and C. It could be 1, 2, 3, whatever. So delta HA is the delta H for one step. Delta HB is the delta H for another step. And delta HC is the delta H for another step. And then if you add up all of the steps, you get the reaction. And if you add up each of their delta H, then you get the delta H for that reaction. Let me show you what I mean. Take a look on page 559. So we're asked to determine the delta H for that reaction. Carbon plus hydrogen makes methane. All right, turn the page. So what you're given these three equations, these three reactions. So carbon reacts with oxygen to make carbon dioxide, hydrogen reacts with oxygen to make water, and then methane reacts with oxygen to make carbon dioxide and water. And you're given the delta H's for each of those three steps. So what Hess's law involves is taking those three equations and combining them in such a way that they will add up to the original equation we started with, which was the carbon plus hydrogen making methane. So question is, how do we add those equations up? Well, if we take a look at the solution, the first equation there at the top of page 560, we'll take that and write it as is. Carbon plus oxygen makes carbon dioxide. Notice that we have carbon dioxide in that equation, but there's no carbon dioxide in this equation, so we need the carbon dioxide to cancel. That's something you want to keep in mind. Second one, so in the second equation, that equation has been multiplied by 2. That's so that we can get rid of the 2 waters that are shown in the third equation. So if you have to multiply an equation by some number, notice there in the solution there, make sure you multiply the delta H by that same number. And so if 1 mole of hydrogen and half a mole of oxygen produce 1 mole of water, about 286 kilojoules of energy is released. If you have twice the amount of water produced, then twice the amount of energy will be released. And then take a look at the third one. In order for the carbon dioxide from the first equation to cancel, the carbon dioxide needs to be on the left side of the third equation. And the methane that we have in our equation here is on the right side. And so the methane in the equation number 3, if you will, at the top of page 560 is on the left. And so we need to flip that equation so that methane is on the right and carbon dioxide and water are on the left so they can cancel. And notice the delta H. So the heat of combustion of methane, methane reacting with oxygen, gives off 890.3 kilojoules of energy. If you take that equation and you flip it around, then that exothermic then reaction turns into an endothermic reaction. So it's a matter of taking these equations that you're given and manipulating them in such a way so that you end up with exactly the equation that you're looking the delta H for. So sometimes that involves multiplying an equation by some coefficient. Whatever you multiply an equation by, make sure to multiply the delta H by the same. Sometimes it involves flipping equations. If you have to flip an equation, make sure to change the sign for delta H. All right, give you a chance for some practice with this. So I apologize, there's no room right underneath number 33 in your notes. So maybe underneath letter D, split that space in 2, and you can do number 33 on one side and number 35 on the other. So let's just do 33, and then we'll go over the answer, and then I'll have you work on 35. So pause now and do number 33. use Hess's law to find the delta H for the equation that you're asked for. So let me start with this up here. This I call the original equation. And so this is what we're looking for. What is the energy associated with this reaction? Now notice this is not a formation reaction. And so we're not going to find the delta H in the back of the book. Those are only for formation reactions. So Hess's law allows us to find the delta H for some reaction that is not a formation or decomposition. And so we're given some equations. And so let's take a look at those. So the first one that I wrote here, that is the opposite of what we are given in the problem. And so I took that equation, flipped it around, and notice that's the delta H changed from negative 16.2 to positive 16.2. The second equation also had to flip that around. So that was written as CaO plus H2O, and I need to flip that. And thus I changed the sign from negative to positive 65.3 kilojoules. And then the third one, again, had to actually flip that one as well, changing the sign of delta H from negative to positive. So this is the answer. So we're going to add up all of our delta H's. So before we can get that though, let's show the work. So this is the work, and you need to show things canceling. So whatever is not in this equation has to cancel. So calcium hydroxide cancels, calcium oxide cancels, and I think that is it. So whatever does not cancel, then we bring down. That's Ca plus 2 plus 2OH minus plus CO2. All of that's on the left side. Makes CaCO3 plus H2O. And what do you notice about this? I call this the final equation. What do you notice about the final equation compared to this here up top, the original equation? Well, they're exactly the same. And if they're not exactly the same, then you messed up. So this is the work, but ultimately what we're trying to determine is this. That is your answer. The energy associated with that reaction, 259.6 kilojoules. This reaction is endothermic. All right, go ahead and pause and apply the same idea, same principle to number 35. Be careful. I think you're going to have to multiply by some fraction coefficients, which is okay. Otherwise, it's not going to work out. So you got to write the equation, calculate delta H for the equation as written, exactly what's shown there in the book. So go ahead and pause and do that now, please. Let's take a look at the solution. Here's what we're trying to find. We're trying to find the standard heat of formation of manganese 4 oxide, MnO2. And so here's our equation. So remember, formation of a substance from its elements in their standard state. So we have manganese and oxygen reacting to make the MnO2. What is the delta H for this reaction? So we're given a couple equations. So notice the first one I have written here is flipped from what we are given in the book. So I took that equation, turned it around because I need the manganese on the left side, because that's where it is over here. It's on the left. And in the original equation given to us, manganese is on the right. So take that equation, flip it around, make the delta H positive 1,792 kilojoules. And then the other equation also had to flip. Actually, no, that one stayed the same. We need oxygen on the left side, and in this equation, oxygen is already on the left side, so we're good there. And then here's where it gets a little bit tricky. So in this equation, we have 3 manganeses, but here we don't want 3. So if you ended up with 3 there, you can't just take your answer, then divide it by 3. You need to manipulate the equations first in order to get this equation here. So in order to get rid of that 3, I need to multiply that whole equation by 1/3. Now, I don't always recommend doing this where you put parentheses around it with that factor outside, because then it gets a little tricky as to what exactly cancels. So normally I have you change each of the coefficients. So that would be a 1, that's a 2/3, that's a 4/3, and that's a 1. Likewise, we have 3 oxygens here. We need 1 oxygen, so we need to multiply that second equation by 1/3, including the delta H value, especially the delta H value. So we get 4/3 here, we get 1 here, and we get 2/3 here. And so what do you notice? 4/3 here, 4/3 here cancels, 2/3 here, 2/3 here cancels, and we're left with 1, 1, and 1. We're going to multiply 1792 by 1/3. We're going to multiply negative 3352 by 1/3. Add those up, and I believe you get negative 52.0 kilojoules or kilojoules per mole of reaction. All right, so there is an alternative way. Whoops, let's go back. Another way that we can use Hess's law to find the heat of reaction, and this way involves using the standard heats of formations of the substances involved in the reaction. So let me, I wasn't able to add superscripts and subscripts, so let's put this in here. So this method involves using the sum of the, that's what this means, right? Sum of the heats of formations of the substances involved in the reaction. And here's how it works. N here, by the way, is moles. So we take the sum of the heats of formation of the products. Again, each multiplied by however many moles there are according to the equation. I'll show you what I mean in just a minute. Minus the sum of the heats of formation of the reactants. Now it has to be in that order, otherwise your sign is going to be wrong. So it's got to be products minus reactants. All right, take a look on page 562. Kind of like a heat content diagram or Born-Haber diagram. So this is why we can use this application of Hess's law. So take the energies of the reactants and products and take their difference, again, products minus reactants, and you can get the net change in the for the reaction, net change in energy. All right, take a look at the example 15.9 right there on that same page. It says calculate delta H for the following reaction. So let's go ahead, let me write this out and kind of walk you through a bit this time just to show you. So you have SiH4, silane, and oxygen, and silicon dioxide is produced along with water. All right, so we need to do products first, products minus reactants. So we take the heat of formation of SiO2, which happens to be negative 910.9 kilojoules per 1 mole. We're going to add that to the heat of formation of water. Now be careful. There's 2 heats of formation of water in the back of the book, one for liquid water and one for gaseous water. So in this reaction, the water is a liquid, so make sure you use that value. Notice though that in this reaction, 2 moles of water is produced. And so we're going to take the heat of formation of water from the back of the book and multiply it by 2. So negative 285.8 kilojoules times 2. So add those 2 together. Minus heat of formation of SiH4, which happens to be 34.3 kilojoules. Add that to the heat of formation of oxygen. Now oxygen is an element. What is the heat of formation for an element in its standard state? How much energy does it take to make O2 from O2? So maybe you notice that in the table in the back of the book, heats of formations for elements in their standard states are 0. So really all we care about when using this method are the compounds involved in the reaction. So delta H, the sum of the delta HFs of the products, each multiplied by their coefficient, minus delta H of the reactants, and you get the delta H for the reaction. which is negative 1,516.8 kilojoules per mole. All right, go ahead and use Hess's law and heats of formation to determine delta H for each of those reactions in number 39. Let's do all three, A, B, and C. Go ahead and pause the video now. All right, here are the setups. I did include the elements, 0 kilojoules. Again, you don't need to do those. I prefer you probably not to do those, but I just wanted to show you that I did not ignore the elements in those reactions. They just have delta HFs of 0. And so there are answers. Be careful of significant figures. So we have no decimal places here. So when we, again, ultimately we're adding and subtracting. So no decimal places in our answer. For this one, we got no decimal places. So again, no decimal places in the answer. And then here and here, those numbers, no decimal places. So no decimal places in the answer. Next, let's take a look at 1510. It's a little different problem. So it says, use the following information to find the heat of formation for lead 2 oxide. And so we're given an equation there, and we're given some delta HFs. So instead of having to use the back of the book, they're giving them to you. And so what's going on this time is we are given the delta H for some reaction, and the delta HFs for all but one of these substances. So again, we're going to apply Hess's law. So going back to this equation here, we know this, and we know all of these and all of these except for one of them. And so we're going to use the heat of reaction to find the heat of formation of one of our substances. In this case, we're going to find the heat of formation of one of the reactants, lead 2 oxide. And so similar setup as before, except we're not solving for delta H for the reaction. So take a look on page 563 at the solution. We have 1 mole of lead 2 oxide involved in the reaction. If there was not just 1 mole, we'd have to take account for that. So instead of solving for X, let's say, we're solving for 2X. This time it's just X, 1X, so we get negative 217.3 kilojoules per mole. All right, try one like that, page 596, number 45. Actually, not exactly like that, but we'll do this one and let's just do A and, let's do A, B, and C. Don't do letter D. Go ahead and pause the video now, please. So here are the equations. What these reactions all have in common. They're all combustion reactions. So technically what we're calculating is something called heat of combustion. So it's specific for a combustion reaction. Generically, we call it heat of reaction. But for a combustion reaction, it's called heat of combustion, which is the energy released during a combustion reaction. And notice how I balance these equations. So heat of combustion is always given in kilojoules per 1 mole of the substance that is burning. So hopefully you got that you balance it that way per 1 mole. If not, then you'll have to make an adjustment in your answers. But it's per 1 mole of the substance that is burning. So that's why I had to use some fraction coefficients there for oxygen. So we can see that the combustion of kerosene is the most exothermic, so it gives off the most energy. That's at least per mole. May not be the case per gram though. If we wanted to, as it asks for in letter D, we can calculate the energy released per gram. We'd use the molar mass of each of those substances. And I didn't work that out, but I'm guessing that this may not be the most exothermic in terms of energy per gram. So that would be something else that you could do later on if you wanted. All right, I think we'll stop there. Next time we'll continue with bond energies. Thanks for watching.